Alrighty, welcome back to operating system. So, talked about basic scheduling yesterday, aka waiting in line, aka taking turns in a queue. So today we get to talk a bit more about scheduling with some advanced scheduling. So the first thing, if you've ever been, we've talked about the Disney World Fast Pass, so that is one thing we could add in. So one wrinkle we can add in for scheduling is adding in priorities. So we may favor some processes over others for any variety of reasons. The simplest way to make this generic is that we can assign each process a priority, and the rules are fairly simple. We run higher priority processes first. We can just round robin processes of equal priority, and this can be done in a preemptive or non-preemptive way depending on what our goals are and what we want. To assign priorities, easiest thing to do is just assign an integer. You can pick lower number means higher priority or higher number means higher priority. So doesn't matter as long as you're inconsistent. In Linux, at least, -20 is the highest priority, so they picked the lower the number, the higher the priority. So that would make for them, again, don't ask me why they made this scale. I don't know why they picked these numbers. 19 is the highest priority, or sorry, 19 is the lowest priority or highest number. So this is how your processes on Linux interact, but by default, you probably just take the default priority and you live with it. So what we want to avoid, remember, is we don't want processes to be starved. If there are a lot of higher priority processes, we don't want there to be a case where the lower priority process will never run. So one solution, if you're the operating system, we won't go into the details, but you might imagine the operating system can just dynamically change the priority. So if a low priority process hasn't executed for a very long time, it can temporarily increase its priority so eventually it gets a turn. A whole lot of different ways you could approach this. This is one solution to that problem. The major issue is if we introduce priorities and they're like dependencies between two processes, so one is waiting on another to maybe do a write or something like that, we have a brand new issue that we didn't have before called priority inversion. So you can accidentally change the priority of a low priority process to a high priority one. And this, you can think of the situation where if a high dependency process or high priority process depends on a low priority process, well then that low priority process should actually be treated as a high priority process because, well, a high priority process is waiting for it to do something. So in order to solve this issue, we can actually implement priority inheritance. So the operating system, that's the one doing all the system calls. It knows what process depends on which. So they can implement priority inheritance to work around this problem. So you inherit the highest priority of the waiting process. So if it has a higher priority than you, now you are a high priority process until that dependency is resolved, and then you go back to the low priority line or something like that. So you would just revert back to the original priority after that dependency is resolved. And this can chain, right? So one process can depend on another, and then that process depends on another. So the operating system would have to do that recursively in order to resolve that dependency chain and mess with the priorities so that, you're not actually, a high priority process isn't depending on a low priority process. So that is one thing we can do. Another thing we can do is we can separate processes into two categories that might have different goals. So we might say, hey, some processes can be foreground processes, and those are things the user is typing into. So that's something you want to have, low response time. You want low response time, good interactivity. While background processes are just things that are running, they're doing a calculation in the background. Maybe you have different concerns for that one. Maybe you only care about throughput. You don't care about response time or anything like that. You just want to finish whatever calculation it's doing. So in Unix, you can have background processes. We won't go into the details this much, but processes also have a process group ID that correlates to its terminal group ID. You don't need to know that specific information, but Linux, because it started a long time ago, has these specific things built into it that they were not able to remove. So they have that notion of it, but it's not really used because most of the time now we just type in Chrome or whatever and have actual graphical user interface. So the idea was nice. It was to separate out processes that users interact with versus processes that they definitely don't interact with. Good idea to separate them because they have different goals. Maybe we can schedule them differently. So what we could do is we can have multiple queues, right? If we want to implement something, I don't know, more, hopefully that might work a bit better. So we could create different queues for foreground and background processes. So like foreground processes could use round robin. Background processes, since we don't really care, we want to keep our scheduling algorithm really, really simple. Try and minimize waiting time. Maybe we just use first come, first serve. And now we would have to, of course, schedule between background processes and foreground processes. So maybe we round robin between the queues, and then after it picks whether it's foreground or background, then it either picks round robin again or first come, first served after that. And we could, of course, make this more complicated and add priorities for them. So maybe you also prioritize foreground tasks more than background tasks. This is to say that there is no correct answer for it. A lot of scheduling is just making something up, testing it, and seeing if it feels good, because everything is a trade-off. There is no one single answer. So this would be a perfectly good thing to do. So, like I said, no right answer, only trade-offs. That's the nice thing about scheduling and the not so nice thing about scheduling. We also haven't talked about what happens if we are scheduling on a computer that has multiple cores. So we'll assume something called SMP, or symmetric multiprocessing. That basically just means all CPUs are connected to the same physical memory. There are more complicated servers and stuff like that where that is absolutely not true. But for this course, we'll just assume most consumer CPUs, all CPU cores are treated the same. They can see the same physical memory and everything like that. And most CPUs have their own private cache, at least at the lowest levels. So they might share at some level, but there's some type of cache that exists on a CPU core. So that is what we will assume for this course. So if we have multiple CPUs, one approach, we can just use the same scheduling algorithm for all CPUs and just tweak it a little bit. So still, we might only have one scheduler, and all it does is it will keep adding processes or just taking processes off the queue as long as there's a CPU sitting around doing nothing. So all we do is we do a slight tweak. Instead of just putting a process on the current CPU, we have multiple CPUs, so we just keep adding them until we're done. So the advantages of this is it has good CPU utilization. If there's any idle processor, we will use it immediately. And it's also fair to all processes if we're just doing round robin. So if you just did round robin with this and just stuck it all on CPU, nice and fair, nothing goes wrong. The disadvantages of this is it's not scalable. Everything blocks on the global scheduler. So what that means is if one CPU core is using the scheduler to try and get the next process, another CPU core can't ask for the same information at the same time. It has to wait until it's made a decision on the first CPU until it gets to have the scheduler make a decision for it. And then the last point is it has poor cache locality. And what that means is whenever your process isn't running anymore and goes on that ready queue, there's no guarantee it will get put on the same CPU. And if it goes back on the same CPU, likely it still has some valid entries in the cache and things like that. So you can reuse that information. Your process will be nice and fast. But if you don't care, you might go to a whole different CPU. You might run on core 1 one time, and then next time slice you run, you might run on core 3, in which case nothing would be cached. Everything would be much, much slower. But this was the approach in Linux like 2.4, which is like 30 years old at this point, or even older, 40 years, something like that. So this is a valid scheduling algorithm, but this was done before when multi-core CPUs were not a common thing. It's just something they added so that it could handle a machine with more than one core. So we could tweak this a little bit and create per CPU schedulers. So now whenever a new process comes in, we just assign it to a CPU, and then each CPU keeps track of its own round-robin queue, and it doesn't depend on any other different CPU. So you have 4 cores. Each core is running round-robin. They each have their own queue of tasks. And then whenever a new process comes in, all your decision is what CPU should this process run on. Advantages to this is it was really easy to implement. If I just had round-robin, I just essentially just made it like a local on a CPU core. Otherwise, I didn't have to change anything. The only new thing I had to write was when a new process comes in, how do I assign it to a CPU? And I could do that in round robin too, or whenever something's free. So other advantages to this is it was scalable. One CPU making a scheduling decision doesn't have to wait on any other CPU making a scheduling decision. So this was nice, scalable. Doesn't matter how many CPUs you have, it runs nice and fast. And it had good cache locality, and what that means is, well, if your process went to sleep or it was done its time slice and it came back, it would be on the same CPU core, so it likely still has the same cache, like the same values in cache, so won't miss anything, things will be nice and fast. The disadvantages of this one, the major disadvantage of this is you only decide what CPU core the process runs on whenever it starts, and then it can't switch back and forth. So you could have some load imbalances. So for example, if say we just have 2 CPU cores and we have, I don't know, 3 new tasks come in, 2 are short and 2 are long, well, we might actually just put the 2 short processes on CPU 1, the 2 long ones on CPU 2, and then eventually this CPU will finish both of them, and then this one is just juggling 2 processes back and forth while the other one is sitting there idle. We can't switch between them. So that's our major disadvantage here, where, hey, we only make a decision whenever a process starts and it doesn't switch CPUs. So we could fix this. Straightforward is we can have some type of compromise between that global and per CPU scheduler. So we can keep a global scheduler that's only job is to rebalance the queues on a CPU. So if it sees a CPU is idle, so like in that case before when core 1 wasn't doing anything anymore, it can just steal a process from another CPU, which is called work stealing. So it just say, hey, you have 2 long-running processes, I'll steal one of them and put it on core 1 that's otherwise idle. So this is getting closer to how your actual system works and schedules things, but you might imagine you might want more control over what processes can switch CPUs and ones that cannot. So some processes you want really good performance on them. They're more sensitive to caches, so if they switch CPU cores, they become really, really slow. So you might want some type of control over this, and that is a concept and an option you can actually apply to your processes, and it is called processor affinity. And that is the preference of a process to be scheduled to the same core. So if you open up Windows Task Manager, if you have something you care about, like, I don't know, like a game or a web browser or something, you can actually set the affinity, and what that means is it will stay on the same CPU core, and it won't change between cores, and it might go a little bit faster. So that work stealing scheduler, that is like a simplified version of the what they called the 01 scheduler that was in Linux 2.6, which is still really old, but can actually do a lot better with multi-core machines. Another strategy, going with the dumb terminology in the course, is we can have gangs now. So another strategy is called gang scheduling. So maybe multiple processes need to be scheduled all together, all simultaneously. This is mostly a thing in high performance computing. That way, the scheduler on each CPU can't operate independently. If you need to, say I have 4 processes and they all need to go on 4 different CPU cores all at the same time, well, I need something global to make that decision for me. So that is what gang scheduling is, sometimes called co-scheduling. So it allows you to just run a set of processes simultaneously. They act as one unit. So this would require like a global context switch across all CPUs. All CPUs need to switch which process they are running. More of a thing in high performance computing. We don't really care about that much in this course, but it's a term that you should know. All right, the other one is real-time scheduling, which is where things get fun. So real-time means there's like some time constraints, either for a deadline or a rate. So for example, audio, it has to happen every sampling period, otherwise you'll get distorted audio and it will sound absolutely horrible. Or maybe autopilot or something like that, something that has a deadline. So you want autopilot to be able to react within, I don't know, a few milliseconds, or it will run over someone. So you probably want it to like actually do something every specified time period. So there are 2 types of real-time systems. One is called hard real-time, where you actually at like a hardware level count the number of CPU cycles, and you have to provide an actual guarantee that you have to prove that a task will complete within a certain amount of time. And that will typically be for like embedded systems and things like that. I don't know, missile controls, fun stuff like that, where like, hey, you actually have to make a decision really, really quick. You have to, and it's like absolutely critical. You have to count the number of CPU cycles, make guarantees. That is not where this course is aimed, because that means you would have to argue about every single thing that could happen on your system. No matter what the situation is, it has to make the guarantee. And on a real complicated operating system that people can launch multiple processes off, I can fork bomb myself, I can do whatever. You can't actually make those guarantees. So what Linux does is it will only do soft real time. And that just means you add a priority and just kind of hope that the critical processes that actually depend on some type of timing, mostly audio, hit their deadline in practice, and then users don't complain, and then it's all good. So you just try your best, you give them high priority, and then that's all good. So Linux will only do soft real time, because if it did hard real time, you would have to argue about every little thing it did and argue about the worst case scenario and that still making some type of deadline. So when we get into scheduling algorithms Linux actually implements is, it actually implements first come, first serve and round robin. So if you search the source tree, you will actually find the first come, first serve scheduler. It's called skeg_FIFO, and round robin, it's just called skeg_RR. And they just have a multi-level queue scheduler for processes of the same priority. And this lets Linux also dynamically adjust the priority if it needs to. And there's basically 2 types of processes on Linux. There are soft real-time processes, and the rule there is it will always schedule the highest priority processes first, and then there's normal processes that just adjust the priority based off some type of aging, which we'll talk in as a bit. But the soft real-time processes, the only scheduling algorithm that's used for those are either real-time or first come, first serve. So scheduling algorithms that are actually used and still used to this day. So real-time processes, like I said, they're always prioritized. So they'll either be first come, first serve or round robin. And there are 100 different static priority levels, 0 to 999, where 0 means the lowest priority and 99 means the highest priority. Annoyingly, normal scheduling policies apply to the other scheduling processes. They're given the enum, the code, schedule normal, and we'll go into what the normal scheduling algorithm is for Linux processes. But for those processes, the default priority is a 0, and the priority ranges from -20 to 19, where a lower number means higher priority, which is fun that these things are not consistent at all. And if you want, your processes can change their own priority with system calls. The system call to change the priority of a normal process is just called nice. So they call the priority of normal processes just to confuse you even more. They call it niceness. So the lower number, the less nice you are, the more CPU you want, if you want to think of it that way. I guess that was their thinking. And there's also like set scheduler if you want to play with the scheduler for your processes. So Linux has a different priority number that tries to unify like the soft real-time processes and normal processes, which is really, really annoying. So the Linux priority goes from -100 to 39, where a lower number means higher priority. And what they do is they also, on their scale, they map soft real-time processes and normal processes on the scale. So soft real-time processes, normally 0 is the lowest priority and 99 is the highest priority. So they just invert it and turn it into -1 all the way to 100. So 99 would be turned into -100 and 0 would be turned into -1, and then the rest of them follow suit. So if you look at the Linux priority number, if it's negative, that means it is a soft real-time process, and the more negative it is, the higher priority it is. On the other side, there's the normal processes that, with the Linux priority, go from 0 or above. So if they're 0 to 39, that means they're a normal process. So they have a niceness score, and their niceness score goes from 0 to -20, and this is how it maps. So it'll just be offset by +20. So if you just add 20 to the niceness score, you get the Linux priority score. I don't know. Don't ask me why they do this. This is like the XKCD joke, if you've ever seen like, this is stupid. Why isn't the standard? Let's create a new competing standard, and then suddenly there's another stupid number scale that doesn't make any sense. So that's basically what this is. So with this, we can actually finally read a bit of what our processes are. So now we can understand, oh, yeah?
I just have a quick question about, for normal processes, like the normal ones.
Yep.
What are some examples of those, and how do we ensure that those aren't the starvation doesn't apply to those?
So starvation will not apply to those. We'll go into what scheduling algorithm they use, but they would use a scheduling algorithm that doesn't allow starvation. Okay. And like your normal processes, if you launch Hello World or anything like that, by default, it would get this niceness of 0. So we'll explore a bit, but yeah, that's what happens by default. You get a 0 niceness or a 20 priority. All right, so we can explore a bit. So if we run htop, we can now read some more columns here. So this column here, this PRY, that's short for priority, and then that's the Linux priority of this scale. So if it's a positive number, it's a normal process. If it's a negative number, it means it's a soft real-time process. And then the niceness, so the next column is here, this NI, short for niceness. So that will just be that top number there. And if it's a normal process, they'll just differ by 20. So we can see that systemd, so PID1, that has a priority of 20. So it's a normal process. And its niceness score is 0. You can see by default, most of your processes just have a niceness score of 0. Some are deemed slightly more important. So like there's this one that has a -4. So that's audit D. So that's something that, I don't know, auditing is important, I guess. So it seems to have a slightly higher priority. It's a -4 or a 20 on the Linux scale. Let's see if we can spy anything else interesting. So here is a process. So its Linux priority, this column, is a -2. That means it's a soft real-time process, which means its niceness is going to be 0 because it doesn't apply. It's just not a normal process. And it seems to be low memory monitor, so that seems to be fairly important. That would be real time to check, if I've run out of memory on my system or not. Let's see if we can find anything. So here's a process that doesn't seem to matter as much. It has a priority of 21, so it has a slightly lower priority than other processes, so we don't seem to care about whatever RT-kit daemon is. So screw that process in particular. Oh, here's one we really don't care about. It's got a priority of 39, aka the lowest priority, or a niceness of 19. And it seems to be also control. You don't know what that is, but that has to do with like sound. Let's see, anything else interesting? We got 20. All right, so here's some more interesting ones. They have a priority of -11, or a niceness of -11, priority of 9. So they have weird names, pipe wire and wire plumber. Linux people aren't that creative with their names. That's software that actually has to do with audio. So audio is important. You have to make your deadlines and everything like that. So they didn't quite go to the level of soft real time, but they just increased their priority. Anything else interesting? All right, there's VS Code taking up a virtual ton of memory. Nothing to see there. All right, we can go to these ones. So these ones are fairly important. So anything in green here, as I'm showing it right now, those are things in the kernel itself. So there seems to be some important things in the kernel. And the only other thing is that thing seems really important. Oops, it's going to move. So this migration 0, that column of priority, if it just says RT, that real time, that has a priority of -100. So it has the most priority of everything whatsoever. And this migration thing, that is the code in the kernel that actually does the context switching. So it needs to happen immediately, so that's why they put at real time. But now we can read some more columns here, right? So any questions about any fun tasks or anything? Yeah. Just something new, we can just go ahead and explore a bit more. But now we know what 2 more columns mean in HTOP, which is always good. So where we are at right now for the Linux scheduler for normal processes. So back in the day in 2.4, that had that big global queue that just doled out processes to CPU cores as they were idle. Then later we got the per CPU core. That was slightly complicated to actually get right. Interactivity had issues, switching processes, work stealing, all of that. And there was actually no guarantee of fairness or anything like that that we could make. We tried our best, but it turned out not to be very good. What the current scheduling algorithm is something called the completely fair scheduler. So the idea behind this is it's supposed to be fair and allow for good interactivity, and that seems to be the best thing we currently have. That seems to work pretty all right. So how does that work? Oh, first, I have to talk about the 01 scheduler having issues with modern processors, modern processes. So back in the day, foreground and background processes was a good division, easy to make. If you had a terminal, it was only connected to one process at a time, so you knew which process your user was interacting with. Less so with a modern operating system with a GUI where you have multiple windows open. Just because you have a window, you don't have a window selected doesn't mean you don't care about it. It might be playing video or something. You don't want frames to skip or audio to go out just because you don't have that window selected. All of our computers can probably do something else while we're watching videos, and we probably have videos open all the time. So a lot harder for the operating system to actually know what a process is actually doing and how much you care about it. So the kernel could try and detect which process you're interacting with some type of heuristics. Maybe if the process sleeps a lot, maybe it might be more interactive, but it's ad hoc. They just kind of make up some characteristics and hope that they hold. It could be unfair. It could misclassify a process. Who knows what it could do? What they wanted to do was introduce fairness for different priority processes. Other ways to think about that, like maybe we just have different sized time slices for different processes depending on how much we care about them. Maybe the higher priority, the larger the time slice. Even if you do that, there are situations where that could be unfair. So what did they try and generalize? What did they settle up on? So to argue about it, you have to argue about like the ideal fair scheduling. So in the ideal case, where we have infinitely small time slices, if we have n processes, each of them get a share of the CPU, they each get a third of the share. So if we have one process, it would just be running that whole time, all on the same CPU. If we have 3 processes, they each get a third of that CPU time. So CPU usage is divided equally between every process, and this would just be for a single core. So here would be an example of the ideal fair scheduling. So say we have 4 processes that all arrive at time 0, and their burst times are 8, 4, 16, and 4. In the ideal case where we're being completely fair and we're ignoring time to context switch and assuming we can share them actually equally, I'll start by dividing all of the segments into blocks of 4. So each column here actually represents 4 units of CPU time. So this would go from 0 to 4 time units. And then in the box, I put in how long each process has been executing for on the same CPU. So if I have 4 processes at time 0, and I have 4 time units, if I was being completely fair, each would execute for a single time unit, just ignoring context switching and everything like that. So everyone okay with that? Diagram's a bit weird, but hopefully it's okay. So in the next column, that's like the next 4 CPU time units. Well, if we were being completely fair, we still have 4 processes, so each of them would run for 1 more time unit, bring up their total runtime each to 1 time unit. And then same thing up until we get to 16. So if we get to 16, if we're being fair to all 4 processes, they would all run for 4 time units. So now at time 16, process 2 and process 4 are done. They wanted to execute for 4 time units. They have executed for 4 time units. So at time 16, we only have 2 processes left, and if they're being fair, they would get half of the total execution time. So that's why between here, these 2 processes jump up by 2 time units. So each column is 4 time units. And in this case, if we only have 2 processes, in order to be fair, they would just divide up those 4 time units in half. So they would both execute for 2 more time units. Same thing for the next interval, 4 time units until process 1 is done. And then there's only 1 process running, so it would get all of those 4 time units each time. So then it would run for 12, and then 16, and then finally it would finish. So that is the absolute fair thing to do. That assumes we can context switch infinitely fast. So this is what the Linux scheduler strives to do, but do it practically because, well, we don't have we can't context switch infinitely fast. So it's fair, every process gets its equal share of the CPU. It would boost interactivity. Because it has the ideal response time, we can switch infinitely fast. But in practice, way too many context switches, it would just take too long. Also, I have to constantly scan all processes, which is O of n, which is slow. I want things to be very, very quick. So the Linux scheduler is something called the completely fair scheduler, and how it works is for each runnable process, it gets assigned a virtual runtime. So that is keeping track of how long it has executed for. And it's saying virtual because it's not real, so it kind of plays with the number. So at each scheduling point, where the process runs for some time t, so that's like their time slice. You increase the virtual runtime by t times some like fudging factor, which is a weight based off the priority. So if it has a default priority, we just account that it ran for t seconds. If it has a higher priority or lower number, we might only say that, okay, you ran for 1 second, but I'll only count half a second against your total runtime. So that is where a lower number actually kind of makes sense as having a higher priority. And then the virtual runtime for each process will monotonically increase. If you haven't seen that fancy math word before, all that means is that the numbers will only ever increase, they will never decrease. So it's keeping track of how long you've executed for. It's just saying you can't go into the negative. It just keeps track of it over and over again. So how the scheduler actually works is it will select the process based off the lowest virtual runtime. So whatever process has been waiting around or whichever process hasn't run in the longest amount of time, then it will pick that process to run, and then it will compute its time slice dynamically based off the ideal fair scheduler. So if it has fallen behind any other process on the system, it will get a larger time slice in order to catch it up to the other processes to be fair. So this, when the process is allowed to run, same idea as before with round robin. Whenever it's done its time slice, then the scheduling algorithm runs again. It would pick the lowest virtual runtime, and that's the next process to run. So it's implemented with red-black trees, so that you probably had to do red-black trees and stuff, but never actually used them for anything useful. This is the first time they're used for something useful probably that you've seen. So all the virtual runtime, all the processes are stored in a red-black tree, which is a self-balancing binary tree, keyed by virtual runtime. So it's O log n, like insertion, deletion, updating, and finding the minimum. So the implementation, it keeps track of the virtual runtime at like nanosecond level granularity. And the nice thing about this is there's nothing, it doesn't need to guess the interactivity of the process at all or anything like that. It just runs the algorithm. It has a few fudging factors like adjusting the weight based off the priority and figuring out the time slice. So those are kind of the fudge factors that we won't go into details with, but that's essentially what it does. And how it works out is it tends to favor I/O bound processes by default. So if it's a process where it just interacts to you pressing a key and then goes to sleep to wait for you to press another key, well, then if it doesn't run for long, its virtual runtime won't increase that much. And then whenever it wants to run again, it has fallen behind any other process on your system. So whenever it gets new input, it will probably run immediately. So small CPU bursts translates to low virtual runtime, in which case it would be scheduled again whenever it is ready the next time. And it would also get a larger time slice in order to catch up to the ideal. So it would be able to process, whatever your keyboard input is and go nice and quick. All right, any questions? So that's basically how the Linux scheduler works. All right, I blasted through that, sweet. All right, so let's wrap up and then I'll hang around for any other questions or anything like that. So we saw scheduling today get a little bit more complex, more than just first come, first serve and round robin. So we introduced priority, then we introduced a problem immediately with priority inversion. So we don't want a high priority process depending on a low priority. We can fix that by just doing priority inheritance. So if there's a dependency, we inherit the priority of the highest dependency process. Then we were like, oh yeah, some processes, maybe a good division is like some need good interactivity, others not so much. Maybe we treat them and schedule them better. That happened back in the day, doesn't happen anymore because systems are much more complicated than that now. Then also we had multiple CPU cores we had to argue about. They basically have per CPU queues. We might also have real time we have to worry about. That requires predictability, so that's why it has very simple scheduling algorithms like first come, first serve and round robin. And then for normal processes, which kind of want to be fair, what Linux uses now is something called the completely fair scheduler that tries to model that ideal fairness. And with that, just remember, bone for you.